Welcome Year 12s to this video. In it, I'm going to take you through the first part of Chapter 9, as you can see. In Chapter 8, we looked at linear growth and decay, geometric growth and decay, and at the start of Chapter 9, we're going to start to see what happens when we combine the two of these. So as you can see, we are going to be using recurrence relations again. But what you'll notice about these kind of recurrence relations is we have our capital R, which is our common ratio when we're talking about geometric terms, but we're actually mixing that with a D value, which is what we used for linear growth and decay. And you'll notice here that we've got an addition and a subtraction symbol together, which basically just means that we could add the D value or we could subtract it when we're combining linear and geometric growth. Now, what are we going to use to, why are we going to use this? The first thing that's going to be really helpful for this to model is reducing balance loans, and that's what this video is going to start off with looking at. Before we do that though, we'll have a look at I guess an example of this recurrence relation being used, but not in a financial context. So this first example here that I wanted to look at was actually looking at the area of an elephant habitat. And so Vn in this case is going to be equal to that area. And we're going to see that area change over time. The area here is measured in square kilometres. And this is over time, where time is in years. So year is represented by n. So what you'll see is the recurrence relation, same form, or I guess the same structure as normal. However, here we have a number being multiplied by Vn, so that's our capital R value, and here we have a value that is being added at each iteration of the recurrence relation. So questions like the following are similar to what we've already been doing. So what's the value initially? What is the value, or what is the area in this case, of the elephant habitat initially? And of course, we just need to have a look at our V0, which is our initial value. Since this is an area, we're going to give a unit as well, which is square kilometres. Okay, so this is where you might like to get your calculator out, because the next question is asking us to describe what's happening to the area of the elephant from year to year. Now, obviously we can see there's actually a couple of things going on. First of all, we're multiplying by R, but you'll notice that R is less than 1, which means that by multiplying by 0.85, we're actually decreasing the size of the area of that elephant habitat by 15%. Since, of course, multiplying by 1 would be an R value of 1, and so to get 0.85, we're actually taking off 0.15, which is equivalent of 15%. So it's decreasing by 15%. However, after that happens, we're actually adding on 500 square kilometres. Now, what you might like to do with your calculator now is have a look, create this sequence in your calculator. So enter 14,000 and then, like we have done with previous sequences, 0.85 times by our answer plus 500. And have a look what's happening to the values overall. Are they increasing or are they decreasing? And what you should find is that it's decreasing. And that's really what we'd like to see with this sort of question, describing what is happening mathematically in the sequence, but also overall what is happening to the area of the elephant habitat. Okay, so write down a calculation to show expected area after 1 year. Okay, so we're going to use the recurrence relation here. It's only after 1 year, so that means we're finding V1. So in your calculator, you will type in 0.85 times 14,000. Of course, that is V0 just there. And then we're going to add 500 onto that. Now, you've already done this in your calculator, actually, because you just had a look at what the numbers were doing. So have a look what happened after you pressed enter just the first time. And you'll see that we get 12,400. Since it said that you need to write down a calculation, you must have this first line here of workings. Now, if you go back to your calculator and you keep pressing enter, we want to see how many times does it take us when we're pressing enter for the sequence to get the elephant habitat drop below 8,000 for the first time. So count how many times, and what you should see is that V6, our habitat has dropped to 7,356. So this means that after 6 years, the elephant habitat has dropped below that area. So that's no financial context at all. And sometimes, of course, we will come across questions where they aren't in that financial scenario. This following one over the page is an example of that. Now, when we say that we're combining linear and geometric growth, the reason we say that is because we've got this capital R and we've got this D value that we're adding or subtracting. Now, what's really important to know or to understand is that when you are combining these, the sequence that you get, so the sequence that you generate, is actually neither. It's neither linear and it's not geometric either. Because remember, for linear sequences, we want a common difference. So common difference if it's linear, and if it's geometric, I'm just going to write geo, we want a common ratio. So if it doesn't have those things, then it's not linear and it's not geometric either. So in the past, there's been a bit of confusion because we're stating here that we're combining the linear and the geometric. So then you sort of think that the sequence will be both of those things. However, when you combine them, you get neither of the two. So the question here is from the sample exam from 2016. It's asking us to generate, or which of these will generate a sequence that is decaying. So that's first important keyword. But the second one is that it's got to be geometric. So what I would do to start off with is have a glance at my options. And since I want something that's geometric, I'll take out anything that's very clearly linear. And so this one here, see how we are subtracting a value, subtracting D, and here we're adding D. That means that those ones there are both linear. One is decay and one is growth. The next thing that I might like to do is, since I'm wanting decay, I could take out anything that's clearly getting bigger. And this one here is clearly showing growth, since we're multiplying by a number greater than 1. So that can't be my answer either. So I'm down to C or E. Now, if you took in what I said earlier, which is that when you combine, so if we were just multiplying by 0.85, yes, that would be geometric. So alone, that would be geometric. And this little bit here, if this was alone, so just subtracting 100, that would be linear. However, combined, have a look at this sequence that's generated. The sequence that you get, obviously starting off with 2000, since they all do, you get 1600 as your next term, and then you get 1260, 971, etc. I won't continue because we won't need to. So the thing about this is, if you have a look at these terms here, think about a common difference. Do we have a common difference here? Well, this is a difference of 400, but then this is a difference of less than 400. So there's no common difference. It's not linear. Now, to test if it was geometric, we would check for a common ratio. So if you do 1600 over 2000, you get 0.8. Now try 1260 over 1600. We actually get a different value. Since these two aren't the same, 0.8, is clearly not the same as 0.7875. We say this is no common ratio. And so we say it's not geometric either. So that's just a little bit of an explanation, I guess, or an example for you to see how this sequence here doesn't give us geometric or linear growth, because we're actually doing two things with the numbers. Our answer is C. Our 0.65, that's clearly decaying. We're multiplying by something less than 1. Okay, so we want to start using our recurrence relation now, and we're going to do this to analyze reducing balance loans. And this is actually going to form a really big part of our the next part of this topic, I guess. We have had a look at compound interest, and I mentioned when we looked at compound interest, when it was looking at loans, that actually when you take out a loan, you would be expected, when you take it out with a bank or a financial institution, to actually start paying it back straight away. Generally, you don't have a loan and then not make any repayments on it. Most commonly, you would start paying it back straight away. And that's what these recurrence relations are going to show us. They're going to show us the interest being added on, because we're going to pay interest with loans. And it's going to show as well our payment being made, which is effectively going to reduce the amount that we owe. It's going to reduce the loan. So reducing balance loans, they are compound interest loans. So we won't be looking at this in terms of simple interest. And there are going to be regular payments made to reduce what we call the principal. Now, the principal is the amount, of course, that you borrowed at the beginning. And so we want to reduce that original amount that we borrowed. We want to reduce it until, of course, we pay it off. So the interest is going to be charged regularly. Now, a lot of the examples are going to have this charged, I guess, monthly or fortnightly. However, just be wary that you can have this for really any time period, and you're going to see a variety of time periods. So the repayments, they nearly always amount to more than the interest for the same period of time. So what I mean by that is when you pay back your repayment, your regular repayment, part of that is going to be paying the interest, but you should be paying back a little bit more than what the interest is, so that you eventually do pay off the loan. The amount that you owe, hopefully, will continue to decrease, provided you make those regular repayments. And that interest, that's always calculated on the current balance, because it's compounding, it's compound interest. So it's always going to be calculated on what you owe at any given time. This means that the amount of interest that you're paying is also decreasing as well. Now, I've just said a lot of stuff, and so we really need to have a look at this mathematically so that we can make a little bit more sense of it. So as you can see, here's our recurrence relation. It's the same one that we used with the elephant habitat before. We've got an R value, we've got a D value. V0 is going to be what we borrowed. It's our principal. And of course, R, capital R here, is going to be calculated by taking our rate, and that's a percentage, so R over 100, and adding that to 1, so that we are increasing by that percentage. Now, D here is actually your payment. The reason it's being subtracted here is because Vn represents the balance. It represents what we owe. And of course, as we make a repayment, the amount that we owe is going to be reducing. So we need to take off D. We need to take off the payment that is being made. Let's have a look at an example that's going to use this first one here. So we've got Paul, and he's buying a bike. And as you can see, it's a $10,000 loan. There's V0. It's over 6 years, and here's our rate, 8% per annum. Now, what's important here is it says interest is debited quarterly. So that's the same as saying that it's compounding quarterly. Just another way of stating it. And he's going to pay it back quarterly as well. So what you'll notice is the regularity of the payments, that should match how often it's compounding. Because generally what you'll see is a payment is made and it compounds at the same time. So quarterly payment, PMT, is a way of shortening payment. and there is our payment there. So this is actually D, our D value. Now, just before we continue, our rate here is at 8% per annum. Now, because it's compounding quarterly, we of course need to make sure we remember to divide that by 4, because we've actually got 2% per quarter that we're being charged in interest. So given that, our capital R value is going to be 1.02. And so our recurrence relation, we're starting off with 10,000 and Vn plus 1. We get that by first adding on the interest, which is done by multiplying by 1.02, and then subtracting the payment that Paul is going to make, 528.71. Now what we can do is we can get our calculator out, we can create a sequence of this, and that sequence we can use to fill in part B. Part B is a table showing the balance of Paul's loan. So obviously when he's made no payments yet, no time has passed, he owes $10,000. So what I'd like you to do is pause me, do this on your calculator, and then I'm going to fill in what you should get in this table. I'm just going to add a $ up here so that I don't have to keep adding it into the column underneath. So do this on your calculator and check that you get the same result. Okay, there we go. Now that is after each of the first, it's actually the first 4 repayments, so a little bit of a typo there, because he hasn't actually made a repayment yet. So if you want, you could add a little one down here, or maybe I'll just fix the typo now and just put a 4 there. So this is actually after first repayment, second, third, and then fourth. Okay, so this next question, why has he not reduced the amount owing by 2114.84, the amount that he's actually repaid after 4 quarters? So what that means is how much has he actually paid them? Well, he's paid them 4 times, what was his payment again? 528.71. So he has paid this amount, which is the 2114.84. So he has paid. But how much he actually paid off the loan here? If we have a look at these two values, so that's what he started owing, and this is what he owes after 4 payments, or 4 quarters. If we have a look at the difference between those two values, what we'll see is he's actually only reduced his loan by this amount. So he's paid over $2,000. However, he's only reduced the loan at this point by $1,300. Now, why has this happened? This happens because every single payment that Paul is making, part of it is actually going towards the interest. It's not paying off the loan. So with every single repayment, you first pay the interest that you've been charged for that compounding period. So each payment that he's made, part of it's first gone to pay how much, or however much interest he's been charged for that quarter. Every payment pays the interest first, then the rest reduces the loan. And that's a really important concept to understand for reducing balance loans, because what we're doing is we're modeling it with a sequence at the moment, and it's not, you can't actually see where the money is going when you do this with a sequence. You can only see how much is owing after each payment is made. Now, what we're going to be doing later in the topic is looking at an amortization table, and that's going to demonstrate where each of the payment, where it's actually going. You'll be able to see the amount of interest and the amount of principal reduction. Before we get to that, we'll just do a little bit of practice with these examples here. So what I want you to do is pause it, and I want you to try these first before I do them. Okay, so once you've had a go, here we have a loan here of $2,000 V0. We have an interest rate of 12% per annum, but you'll see here that it is a loan that's got 8 equal monthly payments, so it's compounding monthly. Remember, that's going to compound when you make a payment. Okay, so that means that our rate is actually going to be 12 divided by 12, so we've actually got a rate of 1% per month. Okay, our recurrence relation to start off with. 1.01 is our capital R value. V0 is 2,000, and then of course we're doing 1.01 times Vn, and the payment is given to us, it's 261, so we're taking off 261. On your calculator, you should have created a sequence after 4 months, which is 4 payments. So 4 months, because it's monthly, that means our N is 4. So every time you press enter, you're going forward in time by 1 month. So 4 months, we want V4, and you should get 1,021.44 to 2 decimal places. Now, these sorts of questions are fairly common, because what you're going to notice is we might be told how long it takes to pay off the loan, but it may not be fully paid off after those 8 months. You might have a tiny little bit left over, and that often happens because we've got to round our payments off, so you're not going to get the perfect amount. Well, in rare cases you will, but you're not always going to pay the loan off exactly in the specified number of payments. So have a look when you get to V8. So after the 8th payment, keep pressing enter on your calculator and have a look what's left over. Because what you should find is that he hasn't paid it off exactly after 8 months. The question states how much will he need to add to the last payment. So what this means is because there's that little bit left over after the 8th payment, instead of waiting another month of being charged interest on that final little bit that's owing, that last little bit's just going to be added to the final payment. And what you should find is that Noah will need to pay, it's not much, but you should get $3.15. And so if you were asked to calculate, say, the final payment, provided it is just paid out after the 8 months, we would add that to that last payment, the 8th payment. Okay, so with this one, we've got a $74,000, so bigger loan this time. It's fortnightly installments. So hopefully what you did was take your 9.75 and divide that by 26. Adjusted is another word for compounded. Here's our payment over here, that's D. And so with our recurrence relation, we've got 9.75 over 26 on 100. And you should get 1.00375. V0 is 74,000. Vn plus 1.00375. That's times Vn. And we're subtracting the payment. There we go. Okay. Now this question here, we haven't really had a look at anything like this yet. I'm going to show you 2 ways to approach this one. So the interest charge before the first repayment. What I mentioned earlier was every time you make a repayment, you'll first charge the interest and your payment that you're making, so your D value, you're going to pay off that interest first, and then the rest is going to pay off the loan. So what we want to know is how much is she actually being charged when she goes to make her first payment. Now, all we need to do is know what the interest rate is for the compounding period, which the interest rate was 0.375. That was per fortnight, and she is paying fortnightly. So if we do that as a percentage of the amount that she owes here, so 0.375% of 74,000, we'll see that the interest she has to pay when she makes that first payment is $277.50. So if you have a look at her payment, it's $323. So a massive amount of her payment is going to go on the interest. $277 worth is on the interest. And then we're going to have a look in part C is how much has actually come off the loan. And you'll see that it's not very much. The other way that you can do this is, of course, multiply by your capital R value. This is a longer way, but you might find it, you might find that you understand a little bit better this way. If I, to generate the next term, I would multiply by R. This is R times Vn, V0 in this case. I would multiply by R and then the payment would be made. So if I have a look at what the number or what the value goes up to, when I multiply by R, I get 74,277. And so the interest must be that amount subtract the principal. And of course we get the same thing, 277.50. Okay, so a lot of interest charged. It was a fairly high interest rate of, what was it, 9.75%. That is really quite high, so that's probably more in line with a credit card at the moment. But of course, historically, interest rates have been quite high in the past for various loans. So if we have a look at the principal repaid, this means how much have you paid off the loan? So we're going to use that phrase a fair bit, principal repaid. How much have you paid off, the loan? Not how much have you paid, she's paid $323.73, but how much has actually come off the loan? So she pays this amount, $323.73, but she was charged in interest to $77.50. So we just need to see the difference. Principal repaid. So 323.73 minus 277.50, and you'll see it's pretty sad. 4,623. Only $46.23 she's paid off the loan after that first repayment. Now what's going to happen is with her next repayment, she owes less. She owes less than $74,000. Only a tiny bit less, only $46 less. But that means that the interest she's charged for the next payment will be a tiny bit smaller. And that means then that the principal she repays is a tiny bit bigger. So as time progresses, the interest will go down, her principal repaid will go up, and eventually she will pay off the $74,000. At the beginning of any reducing balance loan, you are being charged as a percentage, it's the same amount of interest, but as an amount, because you owe the most at the beginning of the loan, the amount of interest that you're paying back is the most at the start of the loan. And this is why you would always be encouraged with a reducing balance loan to pay off as much of it as you can as fast as possible, because that is going to reduce the amount of interest that you're going to be charged. I will see you again in our next lesson where we'll start to have a look at how to model these using a table, and then we'll start to have a look as well at the benefits of the financial solver on our calculator.